Okay, so you recognize these reactions as the definitions are definitions of Bronsted-Lowry definitions of acids and bases. And we talked about the hydronium ion. We talked about the hydroxide ion as being indicators of when things are acidic and or basic. But what I want to point out, and what I pointed out at the end of the video, is that in this case, water is reacting with an acid. So this is an acid-base reaction. Our acid is our acid, and H2O is our base. If this is an acid-base reaction, our base is our base, and H2O is our acid. And so depending on what we react it with, water can be either an acid or a base. And so of course this is true, and this shouldn't probably is not a surprise to you. H2O can act as both an acid or a base. Now, usually it's going to react as one or the other. It's not going to react as both in the same reaction. But this brings us to a really important fundamental reaction of acid-base chemistry, and that is the autoionization of H2O. Okay. So we'll get to the important stuff here, and I'll circle it and put stars around it and all that other stuff. If you take two molecules of liquid water, so H2O liquid plus H2O liquid, and you have them react with each other, one of these can act as an acid and one of these can act as a base. So if this first one reacts as an acid, that means that it's going to create H3O plus. And if the other one reacts as a base, it's going to create OH minus. Right? So we're going to create hydronium and hydroxide in the same reaction. And water molecules just do this to each other, right? So they don't really do very much of it, and we'll see that. But what we can do is we can talk about what is the equilibrium constant for this reaction, right? What is KEQ for this? So you reach back in your mind to the previous weeks and you remember that KEQ comes from, we put the products over the reactants, and so our products are the concentration of H3O plus times the concentration of OH minus. And now the reactants are liquid water, and so we can ignore those. Right? And so those don't factor into our overall equation. And so H3O plus times OH minus, this value is a constant. And that value is 1 times 10 to the negative 14th. This value is so important that it gets its own name. This is the equilibrium constant of the autoionization of water, so we call this KW. This thing here is important. This gets all kinds of stars. And the reason it's important is that this is always true. In every solution where you have water in it, the concentration of H3O plus times the concentration of OH minus equals 1 times 10 to the negative 14th. Now that is a tiny number, and so this equilibrium very much favors the reactants, right? Most of the time, if you have water, it's going to be water, right? You don't take a drink of a glass of water and say, wow, that's a lot of hydronium in that. At least I hope you don't, because it'll probably, that could result in some serious physical damage. But water is water for the vast majority of the time, right? There's a very small amount of hydronium and hydroxide in any solution of water. But however much hydronium we have, the amount of hydroxide is determined by this relationship. If we multiply those two together, we get 1 times 10 to the negative 14th. So if we have a lot of H3O plus, we have an even smaller amount of OH minus. And if we have a lot of OH minus, we have an even smaller amount of H3O plus, because this always has to work out to be 1 times 10 to the negative 14th. All right. So what this tells us is a couple of things. One thing that this tells us is that, right, if we know, and I kind of alluded to this just now, if we know the concentration of H3O plus, then we know the concentration of OH minus. Right? Because those two are related, because this fact is always true, right? So we always know this is true. So if we know one of these numbers, we can figure out the other. So another thing that I'm going to point out is oftentimes just because of shorthand, instead of saying H3O plus, we'll just write it as the concentration of H plus, because essentially you're doing H2O plus H plus. These two expressions, the concentration of H3O plus and the concentration of H plus, these two expressions are always the same. They always mean the same thing. There's never an instance where these are going to be different things. So if you see me use the concentration of H plus, I mean hydronium ion. If you see me use hydronium where someone else uses H plus, that's because those two numbers, those two concentrations are essentially the same. Okay. The other thing that we know is if these two things are equal, right? So if the concentration of H plus equals the concentration of OH minus, right, then that means that both of these have to be 1 times 10 to the negative 7th. And the units on this, I guess, are molarity, right? So, um, and that's just because when we multiply them together, we have to get 1 times 10 to the negative 14th. So we took the square root of 1 times 10 to the negative 14th, we get 1 times 10 to the negative 7th. So when are these two things equal? They're equal when all we have is water around here. And so this, when we have these concentrations here, this is a neutral solution. Right? So a neutral solution always has a concentration of H plus at 1 times 10 to the negative 7th. Or it has a concentration of OH minus at 1 times 10 to the negative 7th. Those two statements are saying the same thing. So one big important fact, concentration of H plus times the concentration of OH minus is always 1 times 10 to the negative 14th, assuming we're in water, right? So remember that fact because we're going to use it. It's going to pop up occasionally when we need it. So you'll see it come back in the next couple of videos and all of that kind of stuff. But remember it because it's going to be important. All right, next up, pH scale. So get excited.